Moving on, our next speaker is Grace Bato. Grace finished her PhD from University Grenoble in France, but she is now a geoscientist with JPL NASA and Caltech. And she'll be talking about remote sensing as applied to volcanism. Grace, your former advisor Mahar is here in the room. And also Betch Payot, Dr. Betch Payot is also in the room. We know that you also did some imaging of Taal when it erupted earlier this year. So I hope you'll also include some more of your analysis about that particular volcanism. Okay, floor is yours, Grace.
Can you see my screen, Sir CP?
Yeah.
Okay. All right. Yeah, so hi everyone, and I hope you are all staying safe and well. Thank you, Dr. CP David and Dr. Bayan Cardenas for kind of organizing this session. I will be talking about volcanoes and satellites in a kind of high-level form of discussion, meaning I will skip all the details of the work, and I will just essentially show some of the important information that we can derive from remote sensing data, particularly radar satellite data that are acquired before, during, and after a volcanic eruption. So I'm not a graduate of NIGS. I graduated from NIP, by the way. So no geology questions, please. Yeah, so here we go. So one of the main goals of volcanology is to be able to deliver a timely and accurate forecast once unrest has been detected. Notable success in forecasting eruptions came mostly from the scientists' ability to discern these repeatable patterns in the seismic data, ground deformation, and gas emission data. And they combine this with the historical and kind of geological evidence of the volcanoes' past eruptive behavior. So here in this slide, I know you are all familiar with this. This is the 1991 Pinatubo eruption in the Philippines. It is one of the most successful, if not the most successful stories in the history of eruption forecasting. Indeed, thousands of people have been evacuated few days before the cataclysmic eruption. To be honest, I do not have a full recollection of this event because I was in the early early formative years of my life then. So if we want to deliver accurate forecasts, we need to first know how the dynamics or the behavior, we need to know the behavior of volcanoes, right? So in general, everything starts from the deep part of the earth. Magma actually migrates toward shallower depth in the form of like melt pockets or a series of dike injections, and you form this so-called magma chamber or magma reservoir. Now, as this chamber is continuously filled with magma, the pressure within this chamber increases, and the system pressure increases as well, and the ground tends to actually inflate. So an excess pressure, also known as the overpressure, can be generated if the pressure within the chamber exceeds the lithostatic pressure or the pressure of the surrounding rock. Now, once the overpressure reaches a critical value, the magma chamber may rupture and a dike may propagate. If there is a sufficient pressure to drive the system, an eruption can actually occur. So note that when the chamber ruptures, the pressure within the system is released and the volcano tends to actually deflate, such that some volcanoes, especially basaltic volcanoes, have this inflation, deflation, predictable behavior. So the ascent of magma towards the Earth's surface often leads to this kind of anomalous signal that we call as precursors, and they can be detected by geochemical and geophysical instruments. This is because as the magma moves towards the surface, it actually interacts with the surrounding rock. So here are the three major monitoring practices carried out by volcano observatories around the world. It includes gas measurement, seismicity, and deformation. Although I acknowledge all the importance of all these monitoring practices, for now I will be just talking about or focus on the detection and monitoring of ground deformation. One is that because ground deformation is a powerful indicator of both the long-term and short-term behavior of volcanoes. Second is that deformation has been used to detect precursors earlier than what volcanic gas and seismic monitoring can. Third is that deformation has a direct relationship to subsurface pressurization. To measure deformation, we can use in situ geodetic techniques and also satellite remote sensing. So when we talk about remote sensing, we basically observe an object from a distance. And in the case of satellite remote sensing, we observe our planet or a planet in general. There are two types of sensors that are placed on board satellites to observe the Earth. One is the passive sensor, which requires natural energy coming from the sun, for example, that can be reflected or absorbed and then re-emitted. So example of satellite systems that have onboard passive sensors are optical satellite systems, such as our very own Diwata 1 satellite. The other type of sensor are called active sensors. They have their own source of energy for illumination. Example of this are radar satellite systems, such as synthetic aperture radar or SAR, which emits microwave frequency. What is cool about SAR is that it works day and night, regardless of any weather condition. SAR, because it emits microwave signal, it can penetrate through clouds. So SAR images are actually formed when microwave signals emitted by the satellite are backscattered by the ground and after it has been illuminated by a radar pulse. So each pixel in a radar image actually contains a complex number, an amplitude, and a phase information. So a SAR image alone cannot give us information about any surface change. You need at least two properly co-registered SAR data captured or taken at two distinct dates. So the first acquisition is used to be called the master image, and the second one is used to be called as the slave image, which you heard it right, are really inappropriate terms. So I joined this community of people advocating for change and to contribute towards equality, diversity, and inclusion in the community. So I also would like to abolish this master-slave terminology. So I prefer calling the first acquisition as the reference image and the second one as the secondary image. So going back, the principle of InSAR exploits the phase differences between the reference and secondary images. If there is a local surface displacement, for example, a volcanic eruption or an earthquake that occurred between the two acquisitions, concentric patterns of signal, or what we call as fringes, can be observed. Here, for example, we know that a volcanic eruption occurred on the 12th of January, and by getting the phase differences of these two images here, we can retrieve a phase map. So the phase map is not directly a displacement map. In fact, a phase map is the sum of the phases that are due to the orbit of the satellite, the topographic change, atmospheric delay, other sources of error, including unwrapping error, and the ground displacement phase. So the ground displacement phase is given by this term here, 4 pi d over lambda, where lambda is the wavelength emitted by the satellite. So in monitoring volcanic unrest, only the phase due to the ground displacement is important, whereas the others are corrected and or are reduced in as much as possible. So in other cases where mapping and possibly quantifying the volume of erupted deposits are of priorities, the phase due to the topography are rather retained. So in order to convert the phase map to discernible units, like in metric units, we unwrap the phase. In the next slides, I will be showing the application of InSAR to volcano studies. I will take the ALF as an example and present key analysis from its pre-eruptive to post-eruptive state. So this is an InSAR image of Taal between January and November 2019, captured by the ALUS-2 Japanese satellite during its ascending orbit. You can see that within the volcano island, you have a distinct one distinct fringe pattern. And note that for ALS2, each fringe corresponds to 11.45 of deformation in the line of sight of the satellite. I'd like to emphasize that InSAR measurements are always along the line of sight of the satellite. So when interpreting an InSAR image, it is always important to know the flight direction of the satellite and its loop direction, so you can have a good interpretation of it. But for now, believe me when I say that the ground actually moved closer to the satellite in this case. So from the ALS2 descending pass, fringes are also visible within the volcano island. As you can see in here, there are two sets of fringe. That is because the descending pass covered a longer period than the ascending pass. This one covered from January 2019 to January 2020. And again, for now, believe me when I say that the ground moved closer to the ground, to the satellite. So if we compute and analyze many interferograms, we can retrieve a time series of the deformation. Here we computed 567 descending Sentinel-1 interferogram covering Taal before its eruption using the JPL's area processing system. From this time series, we can see that there was a general negative trend in the deformation of Taal before it changed course and rapidly increased by late 2018 until the eruption in January 2020. If we look at the ascending time series, we can also observe the similar trend. You have a slight decrease in the trend in terms of the deformation prior to the rapid increase in deformation around late 2018. Here, from the ascending interferograms or pass, we calculated 1,004 interferograms again from the area processing system of JPL. Now, if I take the cumulative deformation 1 year before the eruption from both the ascending and descending time series, say covering this green polygon here, I may be able, or I can model the geometry of the reservoir and its location. And from my model, we find that the reservoir is actually an ellipsoidal reservoir and that it is located at around 5 kilometers depth just below the main crater. We were also able to estimate the pre-eruptive volume change of this reservoir. We measured that the reservoir actually accumulated around 43 million cubic meters in a year. When Taal erupted, we were able to provide InSAR data and analysis to PHEVOX almost in near real time. On the left image here, this is the very first interferogram that we produced and directly communicated internally to PHEVOX during the peak of the eruption in order to help them to plan and provide more analysis. So this map actually shows the extent of how much the ground deformed due to the eruption. For Sentinel-1, each of the fringe here corresponds to 2.8 centimeters of ground movement. Within the volcano island, as you can see, and here in the Pacific River Valley, the deformation are so large that the fringes become dense, so they sort of alias. Interestingly, when I analyzed the amplitude component of the radar data rather than its phase, I was able to produce the map here on the right. And this method is called the pixel offset tracking technique. Using pixel offset, we can better measure those areas within those regions where fringes are so dense and are hard to separate from each other. And notice that here inside the main crater, you have red pixels, and these are actually emplaced volcanic deposits that we believe are from the lava fountaining. And here also in the Pacific River Valley, notice that there's a sharp difference in the direction of the displacement of the satellite. So if I combine the ascending and descending InSAR data, we can actually resolve the horizontal and vertical components of the displacement. So again, I masked the region where fringes are dense because this would lead to phase unwrapping errors. This left image here is the horizontal component. Blue color is towards the west and red is towards the east. The right image is the vertical displacement map. Red means that the ground uplifted, and blue means that it's subsided. So as you can see, there are two distinct signals that we can identify here. One is that the ground opened up by more than a meter in both the east and west directions and inflated by around 0.3 meters. There was also an area of deflation, which is localized here, which is about 0.3 meters. Now, if I model this displacement, the data actually fits very well with a deflating ellipsoidal magma chamber that is consistent with the geometry from the pre-eruptive model, plus a dike. So for the magma chamber, we estimated a volume loss of around 530 million cubic meters. We are also able to estimate the parameters of the dike. We find that the dike is about 21 kilometers by 8 kilometers by 3.7 meters in dimension, assuming a uniform opening. The top depth of this dike is in a very shallow depth, around 300 to 600 meters. If we calculate for the volume of that dike, it's about 0.6 cubic kilometers. And we estimate that if 50% of the volume of that dike were erupted explosively, this is probably a maximum estimate, that could have been a PI4 eruption. But thank goodness that it did not erupt violently. We also did a distributed slip opening to model the dike. So right now, if we look at the state of Taal after its main eruptive phase, we can observe post-eruptive deformation within the volcano island, possibly due to the pressure readjustments as the magma again, as the magma reservoir is now being replenished by new magma input. So on the Pacific River Valley, there are still continuous deformation that you can still observe, which are probably related to the subsurface movement of the dike here. Some take-home messages. I guess we all see that volcanoes are cool, but they are really complex and highly nonlinear. But with sophisticated models and improved observation systems, we are getting better at monitoring and forecasting. So I can't wait for the day that we deliver eruption forecasts the same way that weather forecasts are issued nowadays. And satellites are, of course, amazing. At high altitudes, we can directly observe the Earth and at the same time understand subsurface processes that occurs at depth. Satellites are not designed to replace ground instruments. They deliver complementary information and are both important in the understanding of the behavior of volcanoes. Finally, or last, scientific communication is the key. As remote sensing data become more and more open, there is this increased potential for broad distribution of misinterpreted observations. And this happens all the time in all social media platforms. So we need to, in order to address this, we need to have a community-wide approach that would involve scientists, space agency, and stakeholders. So thank you very much. And I will leave you with this optical data showing Taal's January 2020 eruption.
Great, thanks, Grace.